Hi everyone, my name is Patricio Maturana and the title of this presentation is Bayesian Power Spectral Density Estimation using P-splines with an application to estimating a stochastic gravitational wave background. This is joint work with Renate, Meyer and Christensen. In this presentation I'll talk about power spectral density estimation methods, but particularly our proposal, the P-spline method. We'll start with the definition of the power spectral density function and the components of the Bayesian model used to estimate it. That is the width likelihood and the priors, in particular the Bernstein-Dirichlet and B-spline priors. Later, I'll present our proposal, the P-spline, with its novel knot allocation scheme, which increases significantly the performance of our method. Finally, I'll present an application in estimating the power spectral density function associated to simulated stochastic gravitational wave background. The spectral density is defined as a function of the autocovariance function and describes the power or variance over the individual frequencies of a time series. It is important because we use it to characterize the noise in gravitational wave data and to characterize a stochastic gravitational wave background. Unfortunately, in general, it doesn't have an analytical solution, so it must be estimated. In this presentation, we'll discuss about some Bayesian methods designed to estimate it. The advantage of using Bayesian methods is that they yield the full posterior distribution of the parameters, which allows to quantify easily the uncertainty of the estimates. However, they can be computationally expensive. In this presentation, we'll discuss the Bernstein-Dirichlet process prior, the B-spline-Dirichlet process prior, which are the basis of our proposal, the P-spline prior algorithm. There are other Bayesian methods such as the bias wave that are not considered here, but we will consider in future work. Bayesian models have two components, the distribution of the data, the likelihood, and the prior distribution of the parameter, and the prior on the PSD in our case. For the likelihood, we use the width likelihood, which is an asymptotic approximation of a Gaussian likelihood in the frequency domain. This approximation is based on the asymptotic distribution of the Fourier coefficients. An important characteristic of the width likelihood is that it depends directly on the power spectral density function f, this function, which is the function that we want to estimate. Another important characteristic is that making use of the asymptotic independence of the periodogram ordinates avoids the inversion of a high-dimensional covariance matrix, which would be necessary for the Gaussian likelihood. Thus, the width likelihood has the potential of being more efficient than the Gaussian likelihood. Finally, it yields asymptotically correct inference, even for not Gaussian processes. The methods that we are going to discuss in this presentation rely on the same likelihood but differ on the prior distribution allocated on the PSD, which is what we are going to discuss now. The first prior is the Bernstein-Dirichlet process prior. This prior is based on the Weierstrass theorem, which says that a mixture of beta densities with certain parameters can approximate any continuous density on the interval 0, 1. So this prior is a mixture of k beta densities, where k is variable, which implies that the dimension of the parameter space is variable. Rather than putting a prior on the weights w, whose dimension changes with capital K, the weights are assumed to be induced by a Dirichlet process prior. We test this example in a dataset simulated from autoregressive model of order 4, for which the power spectral density function is completely known and represented in this plot by the continuous line, black line. We estimate this function using the Bernstein-Dirichlet process prior algorithm. The dashed line represents the median of the estimates and the gray area the uniform 90% credible band. We can see that this method is unable to model the second peak of this spectral density, and in general it fails estimating spiky spectral densities. The deficiency of the Bernstein-Dirichlet prior algorithm can be solved by replacing the beta densities by B-spline densities. The B-spline distribution have better approximation properties than the mixture of beta densities. This prior is a mixture of B-spline densities, which densities depends on a number of points known as knots. That is the location where the splines meet. The number of B-splines k is also variable, and like in the Bernstein-Dirichlet prior algorithm, a Dirichlet process is allocated on the weights. In addition, a Dirichlet process is allocated on the knot differences. Here we can see that this method outperforms the Bernstein-Dirichlet prior. So the peaks are clearly captured by the B-splines method. In general, this method is able to model power spectral density functions with abroad peaks. The main advantage of this method is its flexibility. As in our example, and as Edwards et al. Showed in their paper, the B-spline Dirichlet process prior is able to estimate the spiky spectral densities. However, this method is computationally expensive. This is mainly due to the approximation of the two Dirichlet processes, which need to be estimated at each iteration. In addition, the B-spline densities have to be recalculated if the number of or the location of the knots change. In this work, we propose to replace the B-spline by P-splines. The P-splines combine B-spline bases with discrete penalties on the basis coefficients. In addition, we fix the number of P-splines, for instance, using this criterion proposed by Rupert, that is the minimum value of the number of observations divided by 40 divided by 4 or 40 knots. So this seems to work quite well in our examples. Thus, the dimension of the parameter space is fixed. We also specify the knot location and we assign a prior on the weights, avoiding the use of the Dirichlet processes. Since the number of location of the knots is fixed, the B-spline's density needs to be calculated only once. All these considerations simplify dramatically the estimation process, making the P-spline method much faster than the B-spline prior algorithm. So now we need to define the prior on the weights, but instead of allocating a prior directly on the weights, we allocate a normal prior on this parameter v, but we can always obtain the weights applying this transformation. The penalty of the basis of the B-spline basis coefficients is allocated on the covariance matrix of the vector v. This penalty matrix penalizes the inclusion of B-spline densities controlling the smoothness of the Psd estimate. In addition, we define a hierarchical prior for the covariance matrix, where phi is known as the penalty parameter. Considering the width likelihood and the defined priors, we have that the penalty parameter and its hyperparameter have analytical full conditional posterior distributions needed for the Gibbs sampler, so the sampling is straightforward. However, this is not the case for the vector v, for which we have to use the Metropolis-Hastings algorithm to get samples from its posterior distribution. But we can speed up the sampling, for instance, specifying good starting values. Since the weights follows the shape of the true power spectral density function, we use the periodogram to specify good starting values for the weights, making unnecessary the bonding period. In addition, we use pilot posterior samples to specify the proposals in the Metropolis-Hastings algorithm, improving the mixing of the Markov chains. Therefore, the sampling of the posterior distribution of V is sped up. A usual assumption in the P-spline is to consider equidistant knots, like the ones represented by the gray points in the plot. However, here we propose to allocate more knots in those areas in which the Psd function have peaks, in order to assign more computational effort in those areas. Since the true Psd is unknown, we use the periodogram to localize the peak locations and thus distribute the knots according to them. We call this proposal Q-spaced knot location scheme, since it's based on the quantiles of a transformation of the periodogram. In this example, we can see that our approach distributes correctly the knots according to the peaks of the Psd. So look at the black dots in the black points in the plot. We found that this novel approach can improve the P-spline performance significantly. In our example, we can see that the equidistant knots are not able to model the second peak of the PSD, unlike the Q-space knot approach. Here we have the PSD estimate chronologically ordered from left to right. So we have the Bernstein-Dirichlet process prior, the B-spline Dirichlet process prior, and the P-spline prior with Q-space knot. So our P-spline method offers the best estimate among these three methods. We have to highlight that the P-spline performs better in this simulation study in terms of integrated absolute error and computational time. Actually, it's between 4 and 7 times faster than the B-spline Dirichlet prior. Now, we'll apply the P-spline method to the estimation of the stochastic gravitational wave diagram, which is comprised of the superposition of gravitational wave signals from numerous unresolved sources. This can be of astrophysical origin, such as the white dwarf binaries, black hole and neutron star mergers, primordial black holes, or cosmological phenomena. So far, most studies adopted the simplified assumption that the signal is well described by a single power law, characterized by amplitude and slope. However, it is impossible to predict the exact shape of the stochastic gravitational wave spectrum over the whole frequency range. This is why more general and flexible methods are necessary to estimate the stochastic gravitational wave background in PSD. To show the P-spline performance, we will analyze a subset of the LISA data challenge, which contains the simulated data of an isotropic stochastic gravitational wave signal without noise. And here we have the results. This plot displays the periodogram, represented by the continuous gray line, and the median of the P-spline estimate, represented by the continuous black line. As we showed before, the P-spline method is quite flexible modeling PSDs, which is why it's able to model without problem the pronounced curve at high frequencies. An important advantage of Bayesian methods is that we can get the whole distribution of the PSD at any frequency. For instance, this plot shows the distribution of the log PSD at frequency 10 to the minus 2 Hz. From this posterior distribution, we can estimate any characteristic of the PSD function at this particular frequency. As conclusion, the P-spline prior is a quite flexible and competitive Bayesian method to estimate the PSD function. Part of our future work includes to study new knot allocation schemes, which have the potential of improving the performance dramatically, and the extension of the P-spline prior to the locally stationary case, which is a more realistic assumption. The P-spline method is proposed in our paper Bayesian spectral density estimation using P-splines with quantile-based knot placement, which is available on arXiv. Our implementation of the P-spline method is available on my GitHub repository. Thanks for watching.